Our paper looks at mid-eye interaction in casual postures. We study a spherical input space positioned at the elbow level. This input space is independent of body orientation and allows users to reach all corners of the screen without lifting their elbow. Usually, systems use a method that is not flexible enough. By this method, the hand position is tracked on a coordinate system that is aligned with the display. So your hand needs to be facing the display. It's just not very comfortable if you're not sitting straight in front of the display. We first ran an observational study where we asked participants to sit on a couch just as they sit at home. And we gave them commands to do mid-air gestures. For instance, swipe right, left. We found that even when they are in similar postures, participants may do very different motions. We also found that when participants changed their posture, their motions did not change that much. So it seems that the mechanics of mid-air gestures are mostly due to personal preference. Posture did not play a very big role. So, we propose an input space that causes minimum interference to the rested posture. The input space is a spherical surface, and it has two main properties. First, it is defined relative to the elbow joint, so you can be seated in any orientation. And second, the dimensions and geometry match the reach of the forearm when the elbow is rested. The main difference between the spherical and planar input spaces is that the planar space defines a uniform mapping between the world coordinates and the screen coordinates. This mapping is not uniform in the spherical mapping. So if you are controlling your cursor, for instance, the cursor will move much faster towards the top of the screen. To compare these spaces, we designed a controlled study. We had planar input spaces at elbow and shoulder levels, plus the spherical input space. For each condition, our participants selected targets for 5 minutes. We displayed the targets on a large screen in front of the participant. We measure selection time, and we also measure fatigue levels every 30 seconds with the Borg scale. Participants sat on this couch with their arm rested, and we tracked their arms with a motion capture system. We found no significant difference between the performance of the input spaces. The shoulder level planar input space caused much higher fatigue as expected, but at elbow level, we found no differences between the spherical and planar spaces. However, if we plot the performance on the screen space, we see a pronounced weak spot in the spherical space, which is due to non-uniform mapping that I mentioned before. We designed another controlled study to test the performance of the spherical mapping. This time, we had participants in different postures on a couch. Each posture imposes a different constraint, so we wanted to know how interaction is affected by it. This is a trial of the study. We varied target size, target position, and posture. And this time we implemented interaction with a smartwatch. In general, any arm wearable device that has orientation sensors can be used. So our results show that performance is fairly stable across postures. But there are some problematic spots that vary depending on the posture. One interesting pattern is the center targets taking longer than the edge targets. We think this may be caused by the spherical space being asymmetrical relative to the shoulder line. That's because the reachable range is higher on the body side. As a result, the center of the input space is offset from the shoulder line, and that may confuse users. In summary, we found that spherical mapping works well in restful postures and can be easily implemented on a smartwatch. However, we found that unlike a simpler mapping, it has some spatial bottlenecks, which you may have to design your application around.